Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of hydraulic machine subjected to cavitation. So in the last lecture, we have discussed about the cavitation and the effects of cavitation and how to avoid this cavitation or what is the precautions can be taken to avoid the cavitation. That's all these points we have discussed in our last lecture. So in this lecture, we'll see hydraulic machines, what are the hydraulic machines are there and how it is subjected to cavitations. So already we have studied previously in the hydraulic machines. We know that basically we have turbine and another one is pump. So in the turbine, again it is of different types of turbines are there and different types of pumps are there. So in the turbines we have seen that it is of two types based on the energy, that is impulse turbine and another one is reaction turbine. So cavitations will be formed only in the reaction turbine. Cavitations will be only formed in the reaction turbine. And in the pump, only we have discussed about the centrifugal pump. So in the pump also we'll discuss like how it is, how the cavitation is formed and where it is formed. Okay. So first application of this cavitation in the hydraulic machines, that means we'll discuss about the turbine. This is one. So here first point we'll discuss about the turbine. Okay, turbine affected or cavitation in the turbine. You can write this is cavitation in the turbine. Yesterday we have discussed, but in details we have not discussed in that. So cavitation in the turbine actually. So if you remember the turbine, we have few parts are there. Okay, like runner is there. Okay, and we have blades, different like blades are there, and also we have casings. Okay, so the cavitations will occur in this. Which point the cavitation will occur? So in the turbine, the cavitation will be occurred at the outlet of the runner. Outlet of the runner, or we can say outlet of the runner, or we can say inlet of draft tube. There is a draft tube is connected to this inlet of draft tube. So at this point actually our cavitation will be formed, but due to this cavitation formations, okay, that efficiency is going to decrease. So what is the problem in that cavity? Why this if the cavitation will be arised, then what is the issue will be there? What is the problem will be there? Our efficiency is going to decrease. And how this cavitation formed and how to avoid that, already I told in the last class. Okay, so here just I'll tell you that if the cavitation formed, then how to avoid it and how we can identify at which position the cavitation forms. Okay, so due to this cavitation forms, we know that what are the pipes or what are the materials we have selected, so that is going to be wear and tear, or that is going to be you can say that gradually that metals is eaten away. Okay, suppose one pipe is there and the pipe is made of some metals, and though we can see the cavitation formations are there, small bubble formations will be there due to the pressure difference, and this pressure these bubbles are going to anyway it is going to blast. Okay, when it is going to blast, it will release a pressure, and that pressure will effect on the surface of this pipe. Due to small pressure it is affecting, it is going to scratch. Okay, that means this material is going to be eaten away. Okay, so that portion is called as cavitations. So why these cavitations occurs actually? Basically the main reason is the pressure drop. The main reason for this is pressure drop. Pressure drop, or you can say the pressure difference. Okay, the pressure difference. Pressure difference, you can say difference. Okay, now though we have seen that cavitations are formed and it is giving an impact on the turbine and the pump. Now how to like overcome this, or how to identify at which position we can see that cavitations are formed. So for that actually the cavitation, let me tell you, whether or which I told you that at what position, correct? At what position the cavitations are formed. Okay, so for this actually a Thomson's cavitation factor was given. The thing is Thomson's cavitation factor. A term is called Thomson's cavitation factor, which was given by, this is the factor which will define us or which will indicate us that at which position cavitations are formed and how to identify and what is the cavitation value, how we can overcome that. From that we can understand. So Thomson's cavitation factor is named based on the scientist Thomson's, Professor D. Thomson actually, that this Thomson factor actually, this is a dimensionless number. This is a dimensionless number. So why it is dimensionless, that also I'll tell you, and how, what is the role of this, what is that, how to define this also I tell you. So this Professor D. Thomson given a cavitation factor, okay, and that is denoted by sigma. That is denoted by sigma. Thomson's cavitation factor. Okay, so how we can define this, the cavitation factor? Okay, so this is actually defined the available pressure head. We can say the available pressure head which is present, the available pressure head which is present above vapor pressure, above vapor pressure to the operating head, that at what head the turbine is working. Operating head. This is the definition of the Thomson's cavitation factor for the turbine. So how to calculate this or how to identify? So the sigma will be calculated. The sigma we can write, this is, we can write directly H atmospheric pressure. Okay, what is the head at the atmospheric pressure minus what is the head at the vapor pressure minus what is the head at the S, that means suction pressure, divided by operating head, that is nothing but simple H. Okay, so this is the formula for to find out the Thomson's cavitation factor for the turbine case. So here what I can write here, HA. This is the atmospheric pressure head. We can write head. Short form I have written atmospheric pressure head, and head unit we know that is meter. And similarly this is HB. HB we can write what? Vapor pressure head. We can write vapor pressure head, and that also we can write in meter. So what you can see here, pressure head and operating head, so both are head only. So this will be meter, this will be meter, so no dimensions. Okay, no units, no dimensions will be there for this. That's why it is called dimensionless numbers. Okay, similarly, and this is the S. S is nothing but the suction pressure at the outlet condition. The head at the suction pressure at the outlet of the reaction turbine. The head which is present at the suction pressure at the outlet of the turbine. Okay, that is HS. So from these we can able to calculate at which point the cavitation factor. Okay, so in this we need to first identify what is the head value at the pressure level HA, and atmospheric at the pressure atmospheric, what is the head value is there, and at the vapor pressure what is the head value, and at the suction pressure what is the head value is there. Once we need to identify, and this is H equal to, that is net head, or we can say the operating head. So here we can write that is H equal to the net head on the turbine. Net head on the turbine. So this is also in meter. Okay, so actually we know that one more thing, in the reaction turbine we are having two types basically we used to discuss. One is Francis turbine, another one is Kaplan turbine. So the value also for this Thomson cavitation factor also there, the sigma value. Okay, the sigma for the cavitation will be like the value will be there for this factor. This is 0.2 to 0.4. This is for what? This is for Francis turbine. This is for Francis turbine. And the next is, you can write, this is 0.1 to 0.3. This is for the Kaplan turbine. Okay, so this is the value of sigma, the operating cavitation factor for the turbine. Okay, now the question is why we should discuss or why you should read about this. Okay, the thing is to compare, okay, to compare or to identify, to predict or to prevent the cavitation. This thing is required to learn. Which one? The Thomson's cavitation factor. Why? Suppose the question is why he given this factor and this concept. Why is it is required for us? The basic thing is to predict and to compare and to prevent the cavitation in the hydraulic machines. So how we can prevent? When we can identify the problem, then we will try to prevent. Then we can compare it how it is. Okay. So to prevent all these issues in the hydraulic machines, this Thomson's cavitation factor was given. Okay. So one thing you need to remember, what is the definition of this cavitation factor, and for turbine where it is occurs. One is outlet of the runner, another one is inlet of the draft tube. These two are the main issues. Now the second one, this is about the cavitation in the turbine. The second point, cavitation in the pump. Cavitation in centrifugal pump, suppose, because last few classes we are continuously discussing about the centrifugal pump. So let's discuss about the centrifugal pump. Okay. So before going to this centrifugal pump, just I'll give a small hint about this turbine. Okay. So this Thomson's factor, it depends on the which kind of turbine it is. This value is what I told you. Okay. And this actually depends on the different types of turbines. Depends on which kind of turbines. It depends, this sigma c value, if I want to mention, it depends on like type of turbines, which kind of turbines, whether it is a Francis turbine, Kaplan turbine or propeller turbine. Propeller turbine also one of the part in the reaction turbine. So type of turbines, and we can say based on the speed. Okay, based on the specific speed also, and also based on the design and operating methods of the turbine. So that also there. So the sigma c value will be depend on this following parameters. Now the cavitation in the centrifugal pump. So this is also very simple, that how we have identified that where this cavitation occurs basically. Also you have discussed about the cavitation in the centrifugal pump, but again I will give you the hint that where the cavitation formed in the centrifugal pump. So basically at the inlet of the impeller, at inlet of impeller, and along with that the suction side of the pump, suction side of pump. In these two places basically the cavitation occurs. First we need to identify where this occurs basically, then we can identify what is the cavitation value, like what is the factor value is there, and how to overcome that. Okay, first we'll identify the disease, then we'll see why it is occurred, and then we'll go for the precautions or the medicine for that. Similar way also, we can do here, like we need to first identify where this cavitation occurs, then we'll try to find out the value of this Thomson's cavitation factor, then we'll try but which method we can overcome of this one. Okay, so in the centrifugal pump the cavitation will be formed in this, like at this point, inlet of the impeller, or you can say suction side of the pump. So to overcome this, again the Thomson cavitation factor given in formula, similar method. Okay, what formula is given here, same method here also. One formula is there we can write, that is here also sigma. So sigma here I can consider that is NPSS by H. NPSS means what? That net positive suction head. Net positive suction head. So, or we can write this, actually what I have written here, same thing I will write here again, the formula, that P atmospheric minus, sorry, H atmospheric, that means head at the atmosphere level. And similarly, this I can write HB, that is head at the vapor pressure head. And similarly, I can write HS minus H. One more is there. All these heads are there. Along with these, I'll write in small h ls. This is a new term I'll include here. Even in the previous law also, you can include in that also when the losses will be there. Okay, that is called actually losses of head due to the friction. Okay, in the suction pipe. Here actually suction pipe is not there. That's why we are not given. So that's why here it is mentioned, because we have the suction pipe and we have seen that the suction side we are having the cavitations. So how much losses are happened in the suction side, that also we need to subtract it. And what is the total net head? Okay, so this is the formula of this. Okay, and already I told you that H atmospheric, what is the H atmospheric is there, that is atmospheric pressure head in meter of water. Okay, and this is HB equal to, that is vapor pressure head. Already written here the same thing, I am not writing again. And HS is the suction pressure head M of water. And here I'll write one thing, that is HLS. So this HLS is nothing but the head lost due to friction in suction pipe, in the suction pipe. Okay, yeah. So this Thomson cavitation factor sigma, okay, for a particular turbine or pump, if you will consider, will be calculated from this equation. This equation what I shown you, or both of the things we can calculate it for the Thomson cavitation factor can be calculated. This is for pump and this is for turbine, will be calculated. But this sigma value, okay, this sigma value will need to be compared with the sigma critical. This need to be compared. We need to sigma critical, sigma C. So here I have written the sigma C actually. This is the critical value actually we need to consider. So sigma and sigma C, what is sigma is the Thomson cavitation factor, and this is sigma C is the critical value, critical cavitation factor. So let me write here, sigma C is the, this is nothing but critical. So critical in the sense what? Critical cavitation factor. Okay, I'll give you some small example just. Okay, so suppose we'll take a consider of turbine or pump, anything we can consider. In that, let me calculate the sigma value, and I found the sigma value equal to suppose 2. Okay, and there is no cavitations occurring in the pump or turbine. So by this I can say there is no cavitation. Okay, no cavitations formed here. Similarly, again, just after or some place by changing the parameters, I'll get some sigma value 1. Okay, and there also I'm not getting any kind of cavitations. Again, I'll change some parameters, and by that I'll get the sigma value, suppose 0.9, and there we see that cavitation formed. Here you can see that some cavitations are formed. Just I'm giving one example. Okay, so some cavitations are formed. So here the sigma equal to 1, the sigma equal to 1 is called, this is our critical. This is the critical value, or this is the critical cavitation factor for the pump or for the turbine also. Same thing. For both cases we can consider the same thing. So always keep in mind that this is the sigma. Actual sigma is how much? This is sigma critical. So what I want to conclude here, always we need to keep the sigma value, the sigma actual suppose. Okay, or only sigma also you can write. This should be always greater than equal to sigma critical. Sigma critical, so that no cavitations will be formed. at this point we can say cavitations not occurred. Okay, and the second one, what I can write, if suppose the sigma actual, another concept is sigma actual is less than the sigma critical, then here we'll get the results cavitation formation. Cavitation is formed. Okay, this is the basic fundamental things here. Now, why this is required and why these Thomson's cavitation fractures are involved and why it is developed, for what purpose, I hope you understand from this. Now, for this also they are given some empirical formulas are there that you can see in the textbook or you can get from the net also. But the fundamental concept is this. Okay, I hope you understand this lecture, and still if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.